Good morning, students. Today we were discussing in the previous lecture about the atomic packing factor. Okay, the atomic packing factor, it is defined as the ratio of the volume of atoms per unit cell to the volume occupied by the unit cell. And we calculated this APF, or the atomic packing factor, for the simple cubic crystal structure, and we evaluated that the value of APF for a simple cubic structure came out to be 0.52, which means that 52% of the simple cubic structure is occupied by the atoms and the remaining 48% is empty space in simple cubic structure. In this lecture, we will evaluate the values of atomic packing factor for all the basic crystal structures, that is your body centered, face centered, and the hexagonal crystal structure. Okay. So next in line is your atomic packing factor for the second crystal structure, that is the body centered cubic crystal structure. So in the diagram, you can see that on the right hand side, if you see that this is the arrangement of atoms. So we have 8 1 upon 8 atoms on the 8 corners of this unit cell, and then we have a one full atom at the center of the body. So this means that these atoms, they are touching, like they are touching each other, okay, tangentially. So if we see this diagram, this is the three-dimensional diagram. So if we look at this diagram A here, so here you can see that if I look into the diagonal DF diagonal, okay, so what we have here, we have one atom of radius small r, one full semi-atom, the radius will be r plus r2r is there, and then there is another atom at the corner, the radius will be r. Okay. So if you look at the atomic radius, if A is the length of the cube, the edge of the cube, if A is the length of the edge cube, because it is a cube, so it will have all its sides equal to A. So its length will be A, its depth will be A, and its height will be A. Okay. And R is the atomic radius. Then from figure A and B, okay, so the value of DF, जो अभी हमने लिया है, DF will be equal to what? It will be equal to R plus 2R plus R. So it will be equal to R plus 2R plus R. It will be equal to 4R. So DF is equal to 4 times R. So this is obvious from this diagram here. If you look into the diagonal here for the three-dimensional structure, DF will be equal to R plus 2R plus R. So it becomes 4R. Now from the figure C, we can say that C diagram here. So C diagram is this triangle that is DCG. Now here the triangle, it will be this triangle here, DCG, the triangle at the base. Okay, DCG. So it is a right angle triangle. Another triangle, that is D triangle. This is this diagonal. If you look at DF and G, so this triangle here, DF and G. So we have taken two triangles. One is at the base, that is DCG, and another is the triangle formed by this diagonal DF. It is DFG. So we have taken these two triangles. Now these two are both the triangles. They are right angle triangles. So here what we'll have is, you can see here the DC side is side A, length of the side DC is A. So here DC is A, and this side CG is also A. Okay. So from this figure C, you can say that DG square, that is this DG square, okay, that is the hypotenuse here, DG square will be equal to GC square plus CD square, square of both the sides from the Pythagoras theorem. So DG square equal to DC square plus CG square. Now DC and CG, they both are equal to length A. So that is why A square plus A square equals to 2A square. Now again, if you look into the other triangle, that is from the figure D. So here this D is again a right angle triangle. So we can have that DF square will be equal to DG square plus GF square. Okay. So here DF square equals to GDG square plus GF square. Now from this equation 2 on top, we know that DG equals to 2A square. So DG square equals to 2A square. So we can substitute the value of DG square here with 2A square. Okay. And DF from equation number 1, we know that DF is 4R. So we can substitute the value of DF with 4R whole the square. And GF, if you look into this figure, so GF is your this side here, the height of the cube, GF. So this height is again A, because it is a cube, all the sides are equal, so it is equal to A. So GF is A. So here we can substitute GF as A. So we have a equation in terms of radius and side of the cube. So if you solve this, it will be equal to 16 R square equals to 3A square, or we can get a correlation between R and A. So R here will be equal to under root of 3 into A by 4. So this is the required correlation between R and A. Now we can move ahead with the calculation of the atomic packing factor. So here the volume of the unit cell will be equal to the, if we multiply all the sides, that will be A cube. Then volume of one atom, because atom is a sphere, it will be 4 upon 3 pi r cube. Now effective number of atoms in a BCC structure, NEF equals to 2. This we have calculated previously. So the total volume of the atoms in the BCC structure, it will be equal to NEF, that is 2 multiplied by the volume of one of the atom. So it will be 2 into 4 upon 3 pi r cube. It becomes 8 upon 3 pi r cube. So 8 upon 3 pi r cube, it is the volume of the atoms in the unit cell of a BCC structure. So from the definition of the atomic packing factor, so volume of atoms is, we have calculated equation number 5, it is 8 upon 3 pi r cube divided by volume of the unit cell, it is A cube. So here we can substitute the value of R that we have evaluated previously in terms of A, that is R equals to under root 3 A by 4. So it will be 8 upon 3 pi into under root 3 A upon 4 whole to the cube upon A cube. If we calculate this, if we evaluate this, we will get the value of APF equals to 0.68. So this means the APF for a BCC structure is 0.68. That is 68% of the volume of the BCC structure unit cell is occupied by the atoms, and the remaining, that is your 32%, is empty space inside the BCC structure. So this was how we calculate the atomic packing factor for BCC structure. Next, we will look into the atomic packing factor, evaluation of atomic packing factor for the face-centered cubic crystal structure. So in the face-centered cubic structure, what we have here, you can see this diagram on the right hand side. So we have 1 upon 8 atoms at the 8 corners of the unit cell, and we have 6 1 by 2 atoms on the 6 faces of the atom. Okay. So if we look into this diagram B, okay. So here what we have is, if we look into this diagonal DB, so this DB will be equal to what? It will be equal to the, if the radius of atom is R and the side of the cube is A, so DB will be equal to R plus 2R plus R, it will be 4R. Okay. So if we want to evaluate the correlation between A and R, so what we'll do is we will take this edge, that is DBC. So DBC is the right angled triangle here. Now in this right angled triangle, DB square will be equal to BC square plus DC square. Okay. So here DB square will be equal to DC square plus CB square. Now here DB is equal to what? It is equal to R plus 2R plus R. So it will be R plus 2R plus R whole square plus the edge, the side DC will be equal to A square, and BC again will be equal to A square. So it will be A square plus A square. Now if you we will solve this, so what we'll have is 16 square equals to 2A square, or R equals to under the root of 2A by 4. So this is the required correlation between radius of the atom and the side of the unit cell, R and A. Again, we'll go for volume of unit cell. It will be given by A cube. Volume of one atom will be 4 upon 3 pi R cube. In this is face centered. So face centered cubic structure में number of effective जो है, so it will be FCC here. Okay. So number of effective atoms in a FCC structure, it is 4. NEF is 4. So what we'll do is we will multiply this volume of unit cell multiplied by NEF. So it will be 4 into 4 upon 3 pi R cube. So APF is we have the volume of the atoms in the FCC structure, and we have the volume of the unit cell. So we can calculate the value of APF. So we can calculate the value of APF. So here we will have 4 into 4 upon 3 pi R cube divided by A cube. So here what we'll do is we will substitute the value of R that we evaluated previously. It was under the root of 2A by 4. So this value comes out to be, if we solve this equation, so value comes out to be 0.74. So the APF, atomic packing factor, for a FCC structure is 0.74. Okay. Next, we will evaluate this atomic packing factor for the hexagonal closed pack structure or HCP structure. Now in the hexagonal closed pack structure, we have 12 1 by 6 atoms on the 12 corners of this unit cell of a hexagonal closed pack. Okay, plus we have the 2 half atoms at the top surface and the bottom surface, or the face, top face and the bottom face, plus we have 3 full atoms at the center. It is a sandwich. So at the center we have 3 full atoms that are placed between the top and the bottom face. So it's a kind of a sandwich structure. So if you look at this diagram here, this diagram number A, so we have this top face. Okay, so what we'll do is we'll let this edge face the length of the edge, say BH is equal to HG equals to HF, GF equals to FE equals to EK equals to BK equals to A. Okay. So this edge of the face of the hexagonal structure is equal to A, and suppose the height of this unit cell is given by capital C. Okay. So here, if we take this triangle from this structure, so we have taken this triangle, that is this triangle here, HGD. D is the center of this face. So we have taken this triangle HGD. Now this triangle HGD, it is an equilateral triangle. So here all the edges of this triangle are equal to A. So this means all the angles, that is angle at H, angle at G, and angle at D, all will be equal to 60-degree, equal angles. Okay. So if take A is the length of the hexagonal edge and R is the atomic radius, then from figure C here, this figure C here, what we can have, so we have 2 atoms here lying at the edge. Okay. So this means this is one atom. If you see this 3-dimensional diagram on top, so this is one atom and this is second atom. So radius of the atom is R, so it will be equal to R plus R will be 2R equals to A. So from this edge, that is R equals to, so here we will have this that the correlation between A and R will be equal to R equals to A by 2. Okay, so R equals to A by 2 is the correlation. If you see this edge here, this edge, okay, so इस edge के ऊपर क्या है? There are two atoms here, two corner atoms. They are touching each other, and radius of the atom is R. So it will have R plus R. So we will have 2R. 2R equals to the edge length is A. So 2R equals to A. So from here R equals to A by 2. So this is the required correlation, that is R equals to A by 2. That is the correlation between radius of the atom and the edge of the unit cell. From here, the atomic packing factor, to calculate this, so we need to calculate the volume of this unit cell. So for that, what we need to calculate is first the area of the base. If we can calculate the area of this base, okay, then what will happen is we will multiply this area with the height and we will get the volume of this hexagonal unit cell. So for that, what we'll do is, because this triangle is a equilateral triangle, so it will have all its angles equal to 60 degree. So here the angle DHO and OGD, these two angles will be equal to 60 degree. So angle DHG, that is this angle here, DHG equal to angle HGD, and both are equal to what? 60 degree. Now consider triangle DGO. So if we consider this triangle, that is this triangle DGO, this one of the triangles. So this triangle is a right angled triangle. So let the height is A. So it's one of the base edge, it will be equal to A by 2. Uski edge A by 2 हो जाएगी. Okay. So now sine 60 here, sine 60 will be equal to H by A, or here we will have H equals to A sine 60 degree. So it will be A sine 60 degree. So area of this triangle, it will be equal to half base into height. तो इसकी base कितनी है A, height कितनी है H. तो ये पूरे triangle की DGH की half base into height आ जाएगा. तो H की वैल्यू हमने यहाँ पे इवेल्युएट की है ऊपर इक्वेशन नंबर 3 में, it is A into sine 60. So here we will substitute this value of H from this equation number 3. So H is substituted as A sine 60. So we will have A square by 2 into sine 60. So the area of that one triangle, it will be A square by 2 into sine 60. Now this is one triangle area. So how many triangles are there on this base? So we'll have 1, 2, 3, 4, 5, 6. So there are 6 such triangles on the base. So what we'll do, this is the area of one triangle. So as hexagonal base consists of 6 such equilateral triangles, total area of the base will be given by 6 multiplied by A square by 2 into sine 60. It will be 3 A square sine 60. So this comes out to be the area of the base of the hexagonal. So volume of this unit cell, it will be equal to area of the base multiplied by height. So area of the base is 3 A square sine 60 multiplied by height of the unit cell is C. Here the height is C. So we can multiply this area multiplied by the height, we will get the volume of the unit cell. So this is now the volume of the unit cell, that is 3 A square C sine 60. Now volume of one atom, it is 4 upon 3 pi r cube, and effective number of atoms in this HCP structure, it is equal to 6. Okay, so number of effective atoms in the HCP structure is equal to 6. So total volume of the atoms in the HCP structure, it will be equal to 6 multiplied by volume of one atom, 4 upon 3 pi r cube. So from the definition of APF, we substitute the value of the volume of atoms on top and base. We will have the volume of the unit cell, 3 A square C sine 60. So if we simplify this, so we will have pi into A upon 3C into sine 60. Okay. Now this there is this standard value of C by A, that ratio for HCP structure is 1.633. So this is the standard value that we take, that height of the unit cell divided by the side of the unit cell, or the side of the face of the unit cell. of a HCP structure, C by A. So this value, standard value is 1.633. So we substitute this value in this equation number 11. So we will get this equation. If we solve this equation, we will get the value of APF for a HCP structure equals to 0.74. So this is how we evaluate the atomic packing factor for a hexagonal closed pack structure. Okay, after the atomic packing factor, we will move on to the next topic. And okay, after the atomic packing factor, the next topic is what is polymorphism and what is allotropy. Okay. Now, polymorphism is when we change the temperature and pressure for any element, okay, or if that element does not melt, okay, or vaporize. Okay, so what happens is there may be a change in the internal structure of the atom that takes place with temperature. Okay. So this ability of a material to have more than one structure under different temperature and pressure conditions is known as polymorphism. Okay. So if we suppose we have a metal, okay, and if we start heating that metal, so with the increase in temperature at certain stage, what will happen is the internal atomic structure of that atom starts to change. Like it is say normally at say it is a BCC structure, and at certain temperature it changes to FCC structure. Okay, and again it at a certain higher temperature it again changes to BCC structure. So such an material where the change in atomic structure that takes place with the change in temperature or pressure, such a material is known as, or such the ability of such a material to change its structure is known as polymorphism. Okay. Now, if the change is reversible, suppose I heated a metal or a material, okay, and it changed its structure at say 500 degrees centigrade. Again, it changes structure at say 1000 degrees centigrade, and again I started cooling it. So, if the reverse is also possible, okay, so such a material is known as allotrope. Okay, or this ability is known as allotropy. So one is that is the say permanent change is there. So then this means it is polymorphism. And if the change is not permanent, it reverses itself. Then this type of ability of the material is known as allotropy. Now allotropy material is exhibited by iron. This is an example at the bottom here. Now iron exists at room temperature as BCC alpha iron. Okay. So it is BCC structure alpha iron at room temperature. Now when it is heated above 910 degrees centigrade, the crystal structure changes to FCC gamma iron. On further heating to 1400 degrees centigrade, the structure again changes to BCC delta iron, and at 1539 degrees centigrade, this material iron it melts. So these changes are reversible on cooling. So if we start cooling this metal from this melted state back to, if it reaches from 1539 back to 1400 degrees centigrade, the structure will change to BCC delta. If we further reduce the temperature to 910 degrees centigrade, the structure will again change to FCC gamma, and at room temperature again the structure will change to BCC alpha iron. So this means iron is a allotropic material. Similarly, other metals that are polymorphic or allotropic are iron is there, titanium is there, zirconium, and lithium is there. So these are some of the more examples of polymorphic or allotropic materials. So in addition to changes referred above, order, disorder, transformations, and rotations of unsymmetric groups of atoms are also considered polymorphic transformations. In all these cases, total displacement of atoms or groups of atoms is very small, although the inference is often made that these transformations are violent rearrangements. Okay. So one is the whole structure has changed. The other is if small change in the orientation or the disorder or the unsymmetric grouping of atoms, it takes place under the conditions of temperature and pressure. So this is also termed as polymorphism. So this is your concept of polymorphism and allotropy. Okay, the next topic after the polymorphism is what are Miller indices. Now, Miller indices is a system of notations that denotes the orientation of the faces of a crystal and the planes and directions of atom within that crystal. Now, Miller was the scientist who discovered these Miller indices back in 1800s. So he came up with the small notations like this. You can see the diagram below. So this green top surface, okay. So this is a plane. So this plane is denoted by this, you can see a notation in the brackets, it is 001. This means for this plane, uh, x is 0, y is 0, but the value of z is 1 because it is lying at a distance of z. Okay. So this plane is denoted by this notation that is 001. Similarly, this pink plane is denoted by 100 because here the x value is 1 and the value of z and the value of y is 0. Okay. Similarly, this zero plane, this yellow plane is defined by this 010. Okay. So by defining these notations, you can define that which plane we are talking about. Okay. So not only these parallel planes, but we can define inclined planes also by defining these Miller indices. Okay. Plus, these Miller indices also give us these Miller indices for if you take for planes, it will give you the small notations to denote the planes. And in terms of directions, you can also define Miller indices where the direction of atoms can be defined inside the crystal structure by using these Miller indices for the directions also. Now, this is a shorthand notation to describe certain crystallographic directions and planes inside a material. These directions and planes could be in lattices or in the crystal. Now, the number of indices, that is these indices, that is in the brackets. So if it is a one-dimensional plane, so we will define it with only one index. So if it is a two-dimensional plane, we will go for two indices. If it's a three-dimensional plane, we'll go for three indices. And if it is a four-dimensional plane, like in your hexagonal structure, so we will go for four indices to define the direction of the crystallographic plane or the direction of the atomic atoms in the crystal structure. So this is the definition of the Miller indices. Now these are denoted by these brackets. So we have square brackets, we have these angle brackets, normal brackets are there. Okay. So now HKL, if H is any value of X, Y, and Z, HK and L in these brackets, it represents a point. H, comma K, comma L, it will represent a point in this three-dimensional plane axis, that is X, Y, and Z plane. So HKL, that is the value of H in X direction, value of K in Y direction, and value of L in Z direction. So it is in the brackets and separated by commas. Okay. So this describes a point. Okay. When we use commas. Now, negative numbers in the Miller indices, they are denoted by a small bar on top of that number. So if it is minus h, so it will be given by h bar on top. Okay. Now in terms of Miller indices, if we have these square brackets, and there are in these Miller indices we do not have any commas to separate these values. So HKL in square brackets, it will represent the direction. Okay. In these angle brackets, if HKL is defined, it represents the family of these directions. Okay, so we will study about what are family of the direction in proceeding slides. Now, if we have these normal brackets of HKL, it will represent a plane. What plane we are talking about? And if these are HKL is in between these brackets, so it represents the family of planes. So this is basic terminology that is used for describing the Miller indices and what is the significance of each bracket. Okay. So we can have a simple direction, and then we have family of directions. We have a simple plane, and then we have family of planes that can be described by the Miller indices. Okay, the first, if we take into consideration, is Miller indices for, say, we want to describe directions here. Okay. Now, any vector in the lattice, okay, it will start from the origin. Okay, so that vector r can be defined by r1a plus r2b plus r3c, where a, b, c are the basic vectors. Okay, so if we multiply these basic vectors with the say the r1, r2, r3, where r1, r2, r3 are the Miller indices or the fractions. Okay, that can be multiplied with the basic vectors in a, b, and c. A, b, c are the vectors in x, y, and z direction. Okay. So here we have the a, b, and c. Okay. So if we have any, say we here we have r. So if we have this vector that is to this edge here, where this value is 1, 1, 1. Okay. So this vector, it will be defined by r1a. So here r1 will be equal to 1. So it will be 1a plus r2 will be 1. So it will be 1b, and r3 will be 1. It will be 1c. So this vector will be defined by a plus b plus c. So here the Miller indices will be 1, 1, 1. So it will be r1, r2, r3. The Miller indices क्या है? 1, 1, 1 रहेगा. Now again, if we look into this this cubic structure or this cube here, so the point coordinates for unit cell center, if we look at the center, if we go for the center point, okay, now at the center point, the value of x will be 1 by 2, y will be 1 by 2, and z will be 1 by 2. So this means the value of r1a will be a by 2, okay, because here the value of r1 is 1 by 2, r2 is 1 by 2, and r3 is 1 by 2. All are 1 by 2. So the point coordinates will be a by 2, b by 2, and c by 2. So hence the Miller indices for this will be 1 by 2, 1 by 2, 1 by 2. Okay. Now similarly, a point coordinate at the corner will be given by 1, 1, 1. Okay. So this is how we define the Miller indices for the direction. Now let us take an example here. That is, we have this point 0 here, and we want to calculate the value of this vector r, that will be the Miller indices for this vector r. Okay, now we can see that it has in the direction of this say x direction, say its value is 4a, and in the y direction its value is minus 2b. Okay, so this means it can be defined as 4a minus 2b. Okay, so the Miller indices for this will be 4 comma minus 2, or Miller indices will be 4, 2 bar on top. So this bar on top defines minus 2. So the Miller indices for this will be 4, 2 bar. Okay, so this is the how we calculate the Miller indices in two-dimensional plane. Now this two-dimensional plane, this Miller indices starting from the origin 0. Now this index represents a set of all such parallel vectors. So all the vectors that are parallel to R, all can be reduced to this Miller index for that is 4 minus 2. So this Miller index is starting from the origin, that is this R vector, and defined by the Miller index is 4 minus 2. It represents all the vectors that are parallel to this vector. So all these blue lines, now all these blue lines are parallel to this vector R. So this Miller index 4 minus 2, it will represent all such parallel vectors. So this means we need to define one Miller index for the unit cell, and that will define all the values of, or it will represent all the directions and the planes that are parallel to that unit plane, okay, that is in the unit cell. This is how we calculate. Now let us take what is the procedure for calculating the Miller indices for a direction. So what we do is, first step is we take the vector that is repositioned if necessary to pass through the origin. So what we do is we take this vector here. Okay, so here we are taking two examples. One is this brown vector that is touching this point, center point here. Okay, and then there is this red vector that is touching this edge here. Okay, so now read of projections in terms of unit cell dimensions A, B, and C. Okay, now here the value of the R1, R2, R3 in this direction, the value of R1 will be 1. The value of R2 in Y direction will be 0, and the value of R3 in Z direction will be 1 by 2 here. So hence the first example for brown, it is the values of R1 will be 1, R2 will be 0, R3 will be 1 by 2. Okay, now what we do is we will take we will multiply this with the so we will take the LCM of this. So iska jo total common LCM kya aa jayega, 2 is there. Okay, so we will multiply these values with 2. So we will, what we will get is, we will get 2 multiplied by 1 will be 2, 2 multiplied by 0 will be 0, and 2 multiplied by 1 by 2 will be 1. So the Miller index for this point or for this vector will be 2, 0, 1. Okay, now in this case what we'll do is we will find the values of R1, R2, R3 for the vector. So this was where we calculated the values of R1, R2, R3 that defines the vector in A, B, C direction, that is X, Y, Z direction. Okay, so here in this value here, the value of R1 that is in X direction is 1, the value of R2 in Y direction is 0, and the value of R3 in Z direction is 1 by 2. So we'll write down these values of R1, R2, R3, 1, 0, and 1 by 2. Okay, now what we'll do is we need to adjust this to the smallest integer possible. So what we'll do is we'll take the common LCM. So common LCM will be 2. Okay, so when we'll take that common LCM, we will multiply that common LCM, that is 2, with all these values of R1, R2, R3. So iski value aa jayegi meri 2, 0, and 1. So this 2, 0, and 1 will represent the Miller index for this vector. Okay, similarly we'll take another example. So here what we have taken is, we have taken this vector R. Now this is going in, this is the unit cell. So it is going into the another unit cell, that is this dotted unit cell. It is going in the negative X direction. Okay, now in this case for here, the value of X will be in the negative direction, it will be -1. So that is why here -1 is there. In Y direction it will be 1, it is positive 1. In Z direction it will be 1, it is positive 1. So the value of R1, R2, R3 will be -1, 1, and 1. Now these are already the smallest possible integers in this case. So hence the Miller index will be 1 bar 1 1 for this point or for this vector. This is how we calculate the Miller index for the directions. So here this is another example where we have taken the Miller index for the direction for this vector. Okay, so any line or vector direction is specified by minimum 2 points. Okay, so here in a 3-dimensional unit cell, we will define it with the 3 points. Okay, so here that vector will always start from the origin. तो वेक्टर जो है हमेशा हम जीरो से ही स्टार्ट करेंगे. That is the value of origin will be 0 0 0, where the value of x, y and z will be 0 0 and 0. Now what we do is we determine the length of the vector projection in each of the three axes in units or fractions. Okay. Now if we look into this vector here, okay, so here what will be the value of this? So here the value of x is 1, the value of y is 1, but the value of z is 0. So here the value of the fractions or the units will be 1, 1 and 0. Okay. Now multiply or divide by a common factor to reduce the length to the smallest integer value. Here this is already smallest integer value. So in this case, we will enclose this in square brackets, and this will become the Miller indices for the direction of the atom, that is this atom here. So direction of the atom is 1 1 0. Okay. So if the negative number is there, if we go for the opposite side, so the negative numbers will be given by 1 bar. So 1 bar represents negative value. So if the value is negative, so we will go for 1 bar. So this is the procedure for calculating the Miller index in the for the directions. So again we have another example here. So we need to calculate the Miller index for this direction, that is OM is there. So this is the vector OM. We need to calculate the direction. So its value for in x direction will be 1. Okay, x direction में 1 है. In y direction it will be 1 by 2. So x is equal to 1, y is 1 by 2. In z direction it is 0. So it will form a value of 1 1 by 2 0. तो इसमें क्या है, कॉमन एलसीएम 2 आ जाएगा, तो वी विल मल्टीप्लाई विद 2, तो इसकी वैल्यू आ जाएगी 210. तो 210 इज द मिलर इंडेक्स फॉर दिस वेक्टर. Similarly, we can go for this example here. We need to calculate this Miller index for this point, this vector 0 O to this point here. तो इसका क्या आ जाएगा, x की वैल्यू कितनी है इसकी 1 by 2. तो x is 1 by 2. Okay, x की डायरेक्शन में it is 1 by 2, y is 1 by 2 and z is 1. तो ये 1 by 2 1 by 2 1. तो इसमें कॉमन एलसीएम क्या आ जाएगा 2. तो 2 से मल्टीप्लाई कर दो, तो इसकी वैल्यू क्या आ जाएगी 1 1 2. तो द मिलर इंडेक्स विल बी 1 1 2 फॉर दिस. So this is how we calculate the Miller index for the direction.